we're going to begin by setting a working directory. So go to the top menu, Session, Set Working Directory, and choose Directory. And once you're in the right file, open, and we can check that in the console. Now, within the working directory that you've set, you should have a .csv file called example dataset. And we're now going to assign that using the read.csv command to an object called ketone, as we did in session 1. So let's run this line. And let's remind ourselves what's contained within the ketone data frame. And we'll use the head command, which will give us the top 6 entries into the data frame. And we'll use the structure command, which will tell us the number of observations, number of variables, the name of each variable, and the type of data that's contained within each variable. So the goal for today is to learn how to compare two means. And we are going to be comparing body mass in the ketone versus the control group. And we'll do this via 3 steps. Firstly, we'll visualize the data using ggplot. We'll then perform a number of parametric assumption tests. And then assuming we pass these, we'll go on to perform a t-test. So let's begin with visualizing the data. As I say, we'll use ggplot2, the package ggplot2 for this. And this is the go-to package for creating graphs within R. So we installed ggplot2 in session 1, but in case you haven't installed that previously, you can use the install.package command to do so. And then because we started a new session, we'll need to load this from our library. I won't run the install packages command, but I will load it from my library, and we can check that over here in the packages section and see if it's got a tick next to it, and yes it has, so we know it's loaded now. Okay, so this is so ggplot2, that stands for the Grammar of Graphics plot2, and it's an incredibly useful package that allows you to create a huge variety of plots. But its premise is that to do this, you only need to provide 3 components, or each plot is composed of 3 components. And they are, number 1, data, number 2, aesthetics, and number 3, geometry. And we'll go through those in turn. So firstly, we're going to create a histogram with showing the variability in body mass in both the ketone and control groups. So we'll go through the process of creating that histogram using these 3 components. So data is the data frame that we're going to be using. So in this case, ketone. The aesthetics refers to how you want the variables to be visualized. Most importantly, this includes which variables go on which axes, global color, and global shape. And what I mean by global is that any aesthetics such as color and shapes, etc., that are applied here will entered here will apply to the entire graph. And then thirdly, the geometry is the type of graph or any mark on the graph. And what I mean by this is that you could have, for example, a scatter graph, but you'd want to may want to fit a line through your points. So the type of graph would be scatter, and the mark on the graph would be a line of best fit. So let's create our histogram, and hopefully some of this will become clear. So ggplot is the package we're using. Here we have the first component, data, and in this case is the data frame ketone that we created. The second component is the aesthetic, abbreviated to AES, and on this, very simply, the only aesthetic we're applying is that on the x-axis we will plot body mass. So if we run this line of code, you'll see in the right-hand corner under the Plots tab, we have a blank screen. So we have body mass on the x-axis, but we have no histogram yet. And the reason of this is, of course, because we're missing our third component, the geometry. Now, at this point, it's important to know that every graph needs at least one geome or geometry fitted to it, but graphs can have multiple geomes, and I'll come along to explain why that is. Okay, let's move down to line 29. So now we've got the same code as above, but this time we're adding the geome histogram. Now, if you type geome underscore, you'll see that you get a number of options. So these are all the different geomes that you could fit to the ggplot function that you created above. And yeah, you can see the variety there. But for now, we want histogram. So there we go, histogram. Now, if we run this line, there we go. So we've now got a histogram. And it probably needs refining. You'll notice in the console window here, we get a warning about the size of the stat bin, so the intervals that we're using, and they're probably a little bit too small. So we can change that, and let's go ahead and do so. And also, visually, it's not very stimulating at the moment. It's all quite grey. So let's play around with how the histogram looks as well. So if we move down to line 33, you can see much of this is the same. So the ggplot component, so our data and our aesthetic is the same. We're then adding a histogram, but now within the histogram, rather than empty parentheses, we now have bin width equals 5, color equals black, and this refers to the line color because the fill color here will equal white. So if we run that, and there we go. So that looks a little bit better, and we've lost our warning about the bin width. Notice there is a warning here saying that it's removed 60 rows, and this is because if you look at the data frame we're using, we didn't measure body mass at every level of time, so there's lots of NA values in there, so we don't need to worry about the rows being removed. That just means that they're not plotting NAs, which is what we want. Okay, now this graph is looking good. R has handily assigned the X and Y axis titles, but we might want to change those to make it publication ready, and so we can do that. So this time what we're going to do is create an object called bmhist, and now we're going to apply everything to that object. And we'll come on to give an example of why it's useful to actually do that. So we have the same data and aesthetic. We have the same geome. So we've got a geome histogram, same color and bin width as before. But this time we're adding a command called, or a function called xlab. So x label, x-axis label, will be body mass in kilograms. And then we'll add a ylab y-axis label as well, which will be count. So if we now run this, you see nothing happens now because all we've done is assign this to bmhist. So to actually get the graph, we now need to print bmhist. And there we go. So we've got new labels. Now, the key thing with this is learning how to build the graph step by step. But there's a huge amount of information online to help you in this process. And one of the things that is quite useful is ggplot cheat sheet, which I'll show now. Here we go. So this cheat sheet goes through how to build the graph from the data, the aesthetics, etc. But then for each of the geomes here, so for example, we're using geome histogram, and you can find geome histogram presumably in the one variable. So they give you an example here. So they've created an object called A and assigned ggplot, and in this case they're using a data frame that's available to everyone on RStudio that's around about different cars and they're in miles per gallon, for example. So then if you come down to here, so there we go. So we've got this object A and then plus histogram. So you've got the data and the aesthetic contained within the object A, and then you're adding the histogram or the geome. In this case, it's a histogram, and it tells you these are the different arguments that can be contained within geome histogram. So you can change the color, the fill type, the line type, the size, the weighting, etc., etc. So this cheat sheet is quite useful to help guide you through the process of building the graph step by step. Okay, let's remove that. Okay, so finally what we're going to do is save this plot to our working directory. So for that we'll use the ggsave function, and this will in this case save the bmhist object to a file called bodymass.png, which will have a width equal to 5 and a height equal to 5, and this will actually just save the last plot that you created, and it will save it back to your working directory that you set at the beginning of the session. Okay, if we run that, excuse me, we get the same warning down here, but as I say, that's not a problem, but that should have saved to our working directory now. Okay, moving on to box plots. So using the histogram isn't particularly useful in this situation, because actually what we really want to do is find the distribution of body mass in participants for each condition, so ketone and control conditions. So possibly the best way to visualize that is using a box plot. Now, the format for creating or building a box plot is very similar to that which we've done for the histogram. So let's do that. So it's a good idea, I think, when you're building graphs or performing any function really with a data frame, just constantly remind yourself what the variables are called, the formatting, name formatting, etc. So it's, if you use the head command here, so I have capitalized the first letter of the variable names, and that's not always the best approach, particularly given that I haven't been consistent then, and the data frame is called ketone with a lowercase k, so that can generate some errors. So when you're creating the graph or anything else, run the head command, I'd suggest, and just have that available to you so you can make sure that the names of the variables, etc., you're typing in are correct and you won't get errors. Okay, so this time we're assigning the box plot to bmbox. So, excuse me. So try and make these objects intuitive. So body mass underscore box in this case. And so we're assigning using the arrow ggplot. The data in this case again is ketone. The aesthetic is slightly different. So we've got condition is being assigned to the x-axis. Body mass is being assigned to the y-axis, and this time we're using the function fill equals condition, and that means that the color will change depending upon the condition, and by condition we mean ketone or control. And then to this we're adding the geome plot, and so let's run this line and print bmbox. And there we go, we've got a box plot. Now, first task, I'll just hide the answer. So the first task then is to create an object called glue_box and assign a box plot to this showing blood glucose concentrations in the ketone and control groups. So if you use this as a template, but create one as the instructions say, that is looking at the variance in glucose rather than body mass. And it might be good to pause the video here, give yourself as much time as you need, and then I'll scroll down and you can see the answer and make sure it's the same. Okay, so you should have something like this, almost identical, but we've got an object called glue_box, and instead of body mass on the y-axis we've got glucose. So let's run this. And there we go. So unlike body mass, there seems to be some differences between the two groups for glucose. Okay, so previously in this graph we've been using the in the aesthetic component of the plot we've used the fill equals condition function to create or to ensure that the colors aren't the same between conditions, or put in another way that the colors are different between conditions. Now we can change the colors if we're not happy with the color scheme that's been assigned to us. Then we can change the colors scheme manually, and there's lots of different ways you can play around with the colors on your graph, but I find it easiest just to do it manually. So here is an example of why it's good to assign the plot to an object, because rather than having to type all of this out again, or all of this out again, and then doing plus scale fill manual, all we now need to do is add this to the object we've created, because this object already contains all of this. So we're going to use the scale fill manual function, and the values we're assigning, so these are hexadecimal color codes. And now if I switch screens, so these are the different options that are available to you. Huge number of colors. Each color is assigned a code. So you can assign, so let's just take one of these. Copy that. So this is a PDF that I've got saved onto my computer. So we decide we like that color. Let's enter it in here. This would have been gray. And let's run this line. There we go. So we've got the color we've just selected from the hexadecimal color chart. And now we've printed it as glue_box. So actually, here's a point that we should raise. That actually, when we're running this now, this line of code actually produces this plot, whereas before we had to print the glue_box. Now, if we run glue_box, it will go back to our original. So in order to embed this color change into this object, we need to make the following adjustments. So what we're saying here is that we've adjusted the color scheme on the object manually, and now we want to assign this adjustment back to glue_box. So if we run that, now you'll see it won't actually print because all we've done is assign it, but when we now print the object, there we go. So this is now updated, this object is now updated. Okay, so task 2.2, the answer's been on the screen for a while, but using the code above as a template, turn this this plot, so using this as a template, using this as a template, create a violin plot. and assign it to an object called glue_violin. So it is quite straightforward, and just remember that if you type the geom underscore, you'll be presented with lots of options as a clue. So again, it might be worth pausing it here before I scroll down and show the answer. Okay, so you should have something like this. So we've got our object glue_violin, and to that we are assigning ggplot ketone equals our data, our aesthetic is x equals condition, y equals glucose, fill equals condition, plus geom violin. So this is the difference. So if you're unsure, if there's a plot that you want to create but you're unsure of the geom name, just type in geom underscore and then you can search through. So in this case, violin, there we go. So run that, and there we go, we have a violin plot for glucose. Finally, let's add some data points to the figure. So you'll remember at the beginning I said that every graph needs at least one geom assigned to it, but graphs can have more than one geom assigned to it, and this will be an example. So we've already assigned the geom violin, but now we're going to add points, so individual data points. So to do that, we're additionally going to assign geom point. And there we go. So these are the data points, and that's fine. It's somewhat useful, but it's not visually very attractive. So instead of using geom point, we could use geom jitter. And let's see what that does. There we go. So it jitters, as it says, the points, and yeah, it's slightly more attractive, albeit it doesn't necessarily give you any additional information. Okay, so task 3, or 2.3, save the plot to your working directory. And you do that using the ggsave function. And I've called mine glucoseviolin.png. And if you run this line of code, when we go to, or if you go, in fact, let's show that now. So if I just use the session working directory, choose directory, in here, there we go. So we've got that file in there. We can't access it from here because I'm going through the save working directory process, but you can see that this and the previous plot that we made are both saved in there. Okay, let's cancel that. Okay, let's return to the body mass box plot that we created earlier. So remind ourselves of what that looked like. That's fine. Okay, so we might want to know, so box plots are quite useful for identifying outliers, and we can already see on this that there are no outliers. But if there were, as an example of some geom level aesthetic control that you can employ, you could run a line of code like this. So bmbox is our object, and and then to that we're assigning ggplot data equals ketone aesthetic as before, plus geom box plot as before, but now within this geom we have a number of new arguments. So we've got the outlier.color function equals red. So if there are outliers, the color that will be assigned to them will be red. Outlier.shape equals 8, and outlier.size equals 4. Now, obviously, this won't do anything on the body mass chart because there are no outliers. However, task 2.4 is to repeat this, but do it for the variable NIFA. Okay, so we've got a NIFA, an object called NIFA_box. To that we've assigned ggplot, data equals ketone, the aesthetic equals condition on the x, NEFA on the y, and fill again is condition, plus geom is box plot. And now we've actually altered this a little bit, so our outliers will be shown as the color blue, outlier shape will be 4, and outlier size will be 10. Now let's run this line, and there we go. So in the ketone condition we have 3 identified outliers, and in the control condition we have 1. Important to say that these probably aren't actually outliers, as in are produced due to experimental error, but probably actually just reflect biology, individual biology. Okay, so that's us finished on the graph. So now we're going to move on to student t-test assumption testing. So let's start with are there any outliers? Well, we know that's not the case because we just used a box plot to show that. And so number 2, we can move on to number 2. Is there independence of observations? Well, yes, that is the case. There are different populations that are recruited in a random order to the control and ketone groups, so that's fine, we can move on. Normality, are the data in each group distributed normally or normally distributed? So we can test that using the Shapiro-Wilk normality test. Now you'll remember, so to do this, we're going to start by doing this in the ketone group, and at the end of session 1 we use the filter function from the Deepler package. That's DPLYR package, and we're going to use that again here. So here we've got our data frame ketone, and if you remember, this is a pipe, so it means that everything after this applies to ketone, or the data frame ketone. Then we're going to use the filter package, and here what we're saying is filter condition equals ketone. Now if we actually took this away and just ran this line of code, there we go. So we get a data frame now that was just cut down to the ketone condition only. So we've got 40 variables there. We know that there were 80 variables in the original data frame. So that's worked, and now we add an additional pipe, because that means that we've created this filter data frame, and now everything after this applies to the filtered data frame. And to run the Shapiro-Wilk test is very simply a case of Shapiro_test function and the variable that you want to test. So let's run the entire line, and we can see that so we're testing here the assumption that that they are excuse me, the null hypothesis that they are normally distributed, and we can see that the p-value is 0.34, so in that case we can reject that, and apologies, we're testing the null hypothesis that they are not normally distributed. The p is over 0.05, so we can reject that and conclude that in the ketone group, body mass is normally distributed. So next task is to repeat this, but do so for the control group. So using this as your template, determine whether the data in the control group, body mass data within the control group, is normally distributed. So if you pause your video, I'll then show the answer. Okay, so very simple. Instead of having ketone, we just substitute that for control. So let's run that, and very similar, 0.341. Okay, so we can now move on to assumption 4, which is homogeneity of variance. And for this, we'll use the f-test. And that is shown here. So we'll use the variance, var.test function. So to break this down, we've got body mass as a function of condition, and the data equals ketone. So if we run that, okay, so P equals, here we go, so 0.3002. This means there is no significant difference between the variance of the two conditions, ketone versus control. So now we've passed all of the assumption tests and we can move on to actually performing the t-test. Okay, so the t-test, a very similar format to the f-test that we just performed. Here we'll use the t.test function. We have body mass as a function of condition, the data equals ketone, and here variance, equal variance equals true. And we know that because we just tested it using the variance test. So let's run this. And there we go. So down in the console, we have our t-statistic, degrees of freedom, a p-value, which is 0.59, and therefore allows us to reject the null hypothesis. And our confidence, 95% confidence intervals, which certainly straddles zero effect. And here we have summary statistics, so summary mean body mass in the control group and the mean in the ketone group. Okay, so let's say we wanted to run this, we wanted to perform multiple t-tests on data within a data frame. Rather than having to perform this line of code for each, not that it would be a huge burden, but rather than having to do it individually, we can use the lapply function seen here, and we're going to compare beta-hydroxybutyrate, glucose, and NEFA. So we're going to perform 3 t-tests, and we're comparing these concentrations between the ketone and control groups. So if we run that, here we go. So for each variable, so we've got beta-hydroxybutyrate. Is there a difference? Yes, there is. Glucose, yes, we have a difference. And NEFA, yes, we have a difference. However, of course, this isn't, if we go back to our data frame, what we've done there is compare all of the beta-hydroxybutyrate, for example, values, regardless of time, in the ketone versus control group. And what we are actually interested in is looking how this changes as a function of time. So what we need to do is perform a two-way ANOVA with post-hoc comparisons to do that. And that will be the subject of session 3. Remember to save your work, and I'd recommend repeating these the steps that we've gone through here with your own data, just so you can get a handle on it and practice with it. One last thing to mention, at the end of each session, it's quite good to clear your global environment, your plots, and the console. So to clear the console, on the Mac at least, it's Control L. I think it's the same on Windows. On the plots, you can use this little broom up here, and that will clear those, and the same again on the global environment. And then we are done.